Alright, so this is a lesson for 8.5. So I'm going to describe what's happening in this GIF. So this guy is hitting a tuning fork. Right, so he's going to hit a tuning fork. It's going to make a sound. If you don't know what a tuning fork is, I would suggest Googling what a tuning fork looks like. Alright, so he's hitting a tuning fork, it's vibrating, it's creating sound waves. Now, if you look at the beginning here, you'll see on the top, in the right hand corner, you'll see that the ball is kind of just stationary. It's kind of just moving back and forth, and there's another tuning fork on the other side. Now, when he hits the first tuning fork, what do you see happen? Well, you see ball being hit, and then it keeps going to the right. And why does that happen? Well, the fact that you're hitting its first tuning fork, creating sound waves, causes the second tuning fork to vibrate. And once the second tuning fork vibrates, well, then the vibration hits the ball and causes the ball to move outward. And this is something known as resonance. And I think a lot of you guys have kind of heard about it before, right? If you've ever heard like an opera singer or someone kind of break glass just by using their voice, just by singing. So that is possible. Right? That is possible. That can be done, and I'm gonna show you here. And it might get a little bit loud. It might get a little bit noisy. So be aware. Let's turn around down. So you'll see that this glass is vibrating. Right? You don't really doesn't really make sense. A glass vibrating, a glass moving back and forth, but you do see it here, and you see the vibrations increase as time goes on. Eventually, up to a point where it will eventually break. Right? It will eventually break. Right? And that's called resonance. And so, why does that happen? Right? Why does that happen? Take a look at this. Take a look. So you'll see here, and objects vibrate at a natural frequency, right? There's always a certain frequency that objects vibrate at. Kind of like if you kind of think of it as a kid on the swing, and you're moving back and forth, everything's vibrating at a certain frequency. Now, what happens? Well, if we add a wave, right? Think of constructive interference. We add another wave on top of that. And so let's say a wave vibrates, rather, let's say a glass or object vibrates at this frequency, right? So that's the frequency it vibrates at. Well, what happens if we add sound waves that kind of vibrate at the same exact frequency that maybe they don't really have the same amplitude, right? They don't have the same energy, and so they you add another sound wave here, but they aren't as large, right? So you add it with the same exact frequency. And if you add both of these waves, right, if you put both of these waves on top of each other, well, what happens is, well, they're going to create a larger wave with a larger amplitude. Whoa, where did it go? Where did it go? Right, so it creates another wave with a much larger amplitude, right? Because you're combining these waves, right? You're combining them. And as you add more sound waves to the object, well, the object vibrates more and more and more. As you saw in the glass, it vibrates more and more and more as you increase the amount of sound waves that hit the object. Think of it like a swing. A kid is on a swing. He's vibrating. You can represent it as a wave. He's going back and forth, back and forth. And each time you push this kid, he kind of goes further. Right, this is the he pushes, and then you push, and then he goes a little bit further, and then you push even more, and he goes even further at that point. And you push even more, and so that's kind of what's happening to an object, to the glass, when it breaks. You're adding more waves of the same exact frequency, making it vibrate so much that the glass will eventually break. And this is known as resonance. You're adding waves of equal frequency. And let's look at this video. Right, this kind of video kind of shows you it.
I think this is one of the few cases where it's easier to learn a trick if you understand the physics. Also, I learned some major tips along the way, including the obvious ones like wear safety goggles and don't try to trick. The reason this is so challenging is that the note that you have to play has to be the glass's exact resonant frequency. We'll get to resonant frequencies, but first we need to think of the glass not as something that you drink out of, but as an oscillating system. An oscillating system is a system that goes back and forth, like a playground swing. I know that back and forth is a vague definition, but there are so many different types of oscillating systems to get more specific ones. Electrically and magnetically oscillating systems, economically oscillating systems, like an economy that goes up and down. But mechanically, these are all oscillating systems. So when you flick a wine glass, it vibrates back and forth, pushing the air, and that's what makes the ringing note that you hear. And back to the playground swing. The swing is a totally overused analogy for explaining resonance, but it's just so good. It's an oscillating system, and it has a resonant frequency. You can describe resonant frequency two ways. One is that it's the frequency your swing will keep swinging at if you just let it go. In the wine glass, that frequency is the note it vibrates at if you push it and let it ring. By the way, musical notes can always.
So that's our natural frequency of the glass, right? It vibrates at that frequency, makes that sound wave. And if you want to add to that frequency, right, if you want to make it vibrate even more, you have to mimic a sound that is that frequency.
Another way of describing resonant frequency is that if you drive your oscillating system at that frequency, it will have the maximum response in amplitude, meaning it'll have the maximum response in distance between the back and forth. So if you push the swing at just the right moment, or in other words, you match its resonant frequency, the amplitude will increase. I know you've done this, and it'll increase more than if you pushed it at any other frequency. Now, the wine glass analog is that if you sing at the glass at its resonant frequency, your vocal cords are vibrating the air molecules that vibrate the glass and drive it at its resonant frequency. And then just like the swing will go higher and higher, the glass will vibrate or shake harder and harder. And if you shake something hard enough, it will eventually break. So that's why this is so tricky. You have to sing at the exact right frequency and hold it really loudly. I can't break this particular glass, no matter how hard I try, because I can't hold that note loud enough. So it's called Snell physics, and also to be able to match the right pitch. I should probably disclose that I did some musical.
All right. So then you have to match the resonant frequency, the natural frequency of whatever object you're trying to break. Otherwise, the waves won't be in sync, they won't constructively interfere, they won't add each other, and you won't have enough of an amplitude. So now that we've done with resonance, and so let's talk about diffraction. So diffraction is essentially, well, think about it. You guys know how loud I sound in the classroom, right? People can hear me all the way down the hall. So how do people hear me, right? Because sound needs to travel somehow. How is it that people down the hall can hear my sound, right? My voice. And the reason is because sound waves can kind of bend and curve. Well, let's take a look at the bottom GIF over here, right? Let's get a look at the bottom GIF. You'll see that as the sound waves kind of go through this doorway, they kind of spread, right? They kind of spread outwards, and this is actually known as something called diffraction. Right? Diffraction is essentially the change in direction and propagation of a wave around the barrier or a small opening. And you can all see examples of diffraction over here. Again, as waves move towards an opening or around the barrier, the wave will kind of curve. It will kind of make this some kind of circle. Now, there are really two important things here, right? So the larger, let's compare a large opening and a small opening. A smaller opening will give you a larger diffraction, right? You will get a larger spread, you will get a better spread. And a small, rather a large opening will give you less of a spread. Well, you'll get a smaller diffraction. All right, so that's one thing you should know, like these large opening versus small. Now let's compare a small wavelength with a larger wavelength. It's the same opening, right? So the same diameter opening, same opening, but the bottom one has a larger diameter, a larger wavelength. And the larger your wavelength, well, the better the spread of your diffraction. So you'll have a greater diffraction if you have a larger wavelength, as opposed to smaller wavelength, right? So there are two different factors that affect a diffraction. It's the opening of whatever your wave is traveling through, and the wavelength of your wave. So those are the two things that matter. And you'll real also, there's something important, is that the wavelength of the incoming waves is equal to the wavelength of your outgoing waves. Okay, so your wavelengths are equal. They do not change, right? That's something very important. Something not necessary to know, but is kind of nice, is that, well, let's say Wi-Fi, right? Wi-Fi is a wave, information travels in a wave. And when they say 5G, 4G, they mean in terms of frequency. 5 gigahertz, and that's the frequency of your wave. 5 gigahertz, so the blue line would be your 5G wave, right? You'd have more waves in a given amount of time. And the red line represents 2.4G, which essentially means, well, you have less waves in a given amount of time. And while radio waves, Wi-Fi, radio waves can pass through objects and barriers, but they can also diffract, right? So any type of wave can diffract. For example, your phone, right? So you use a flashlight. Your flashlight comes out from a small opening and spreads. That's diffraction. Light is a wave. So we have a practice question here. Parallel wavefronts are incident on an opening in a barrier, which diagram shows the configuration of wavefronts and barrier opening that will result in the greatest diffraction of waves. Again, if you want the greatest diffraction, you want the smallest opening, right? So you want the smallest opening. All right, so which kind of means C and D are incorrect, and you want the largest. Wavelength. So it's going to be B. Okay? Small opening, largest wavelength, which B shows. B says, which diagram best represents the appearance of wavefronts after passing through the opening in the barrier? Well, you kind of know they have to kind of make a curve, right? So as they're exiting, you kind of have to make a curve. So it's neither D, C, or D. And the wavelength of these waves, right? So they must be equal. The incoming wavelengths must be equal to the outgoing. So it is going to be A. Cannot be B. So law of reflection, we did this in the lab when we talked about law of reflection. So let's say you have a surface. Right, let's say you have a surface let's say, I don't know, this is the mirror, right? So this is the mirror. And very important here is that we always kind of draw something that's called a normal line. A normal line is an imaginary line that is perpendicular to the surface of whatever your wave is bouncing off of, right? So here we have the incident wave, incident light wave. So light wave is coming in, right? So at an incident angle, we call this the incident angle. And so this, and then the wave it makes, right, it gets reflected. Well, it kind of, the angle it makes in reference to your normal line is equal to your incident angle. And that's the law of reflection. The angles are equal in reference to your normal line. And again, your normal line is perpendicular to the surface. Right, so here was the angle of the reflection. If you think about it, what is the angle of reflection here? Right, you'll know that this is your normal line. So the angle it makes in reference to your normal line is equal. So it's 60 degrees there. That's your angle of reflection. Now 5b is a little bit trickier. You have incident wave that travels towards this barrier, and they want to know the direction of travel for the wave after being reflected. Well, first you have to figure out what your normal line is. Your normal line is B. Your normal line. This is your normal line, right? Because this is your barrier. It's bouncing off the barrier, and your normal line is perpendicular to your barrier. Your wave is moving this way, so this is your incident wave. So that must mean this is your angle of incidence. And we know that the law of reflection says that, well, my angle of incidence is equal to my angle of reflection. So both of these angles must be equal. So your wave will travel in the direction of C. All right.